Okay, hello everyone. So as you can notice, this year Unite we have a lot of talk about Unity dots, and the former name is Unity ECS. And so this session is also about a project, more like a case study. What do we achieve and how do we do it with Unity ECS? The project is Metropolis Traffic Simulator. So first, I'll talk a bit about myself. My name is Pham, and I've been a software developer with about more or less 10 plus years of gaming industry experience. I've been working in many game companies. For example, Konami from Singapore, and then I moved to Europe, work on Big Point in Germany. At the moment, I'm a senior developer at InnoGames, based in Hamburg, Germany. We are like a company of around 400 employees. And as you can see, this is a mouthful of technology, so I'll just shorthand it to ECS. And this technology promised to give you very high performance, and that would enable you to build a massive scaled game world. And all of that is, at the moment, not possible with the regular Unity that you are used to. And Unity itself demonstrates that by their very impressive demos, the Nordius demo and the Mega City demos. As you can see, from the pictures, you see a lot of soldiers, a lot of arrows, lots of buildings, lots of flying cars. So the focus of their demos is basically to deliver their promise about high performance, about massive scale. And I think they delivered that spectacularly. However, when you look closely, the gameplay complexity is not their focus. When you look at, let's say, the arrow volley, the soldier in a square formation basically just shoot a square arrows. And also on the Mega City, the flying cars kind of following a fixed, predefined patterns without too much pathfinding going on. And as you can also see, the trend that when Unity developed ECS or DOTS, they first released the very early version that fulfilled the promise of giving a very high performance, and then from there, they get the feedback from developers like us to improve in terms of gameplay complexity. And there are a few examples about this. For example, when they released system state components, it allowed us developers to detect entity addition and deletion, which is something that very obvious how we can do in regular Unity. And around late last year, early this year, they released dynamic buffers, which basically allows you to store data in array form per entity, which is also something that we take for granted in Unity regular. So we can see the patterns here that Unity ECS is kind of catching up with Unity regular in terms of gameplay complexity. And also during this keynote, you all know that they will convert more and more of Unity feature to dots. So from the perspective of the game companies, how this cutting-edge technology would benefit our games. Looking at this portfolio, for example, on the left side, you see Forge of Empire, which at the moment is the biggest browser game in the world, and also has a very successful mobile version. The one on the right, Warlord of Thanem, is the one I'm working on. And basically, at the entire lineup, they are all simulation-heavy game with a very deep gameplay mechanic. That would pose a big challenge to Unity ECS. And as a company, we always try to look forward to cutting-edge technology and how that would benefit us to develop future games or adding feature into our existing game. The question remains that whether it is possible to create complex gameplay, and how do we solve common problems in the ECS way? Because when Unity introduced ECS, it brings two new things to the table at once: the entity component system and the data-oriented design. To us, programmers that are used to the regular Unity and the object-oriented way of programming, that's a steep learning curve. Common problems like pathfinding or collisions are not trivial in ECS. Collision here, I did not mention about the Unity physics, but just normal collision. For example, if you have a grid and a few units moving on the grid, checking collision between them in Unity ECS is not trivial. And that's why the traffic simulation project was born, basically as a case study, and we try to push as far as we could in terms of gameplay complexity. I will switch to the phone now to show the result. So let's take a look at a simple scenario. So here we have a small intersection, and the vehicle was spawned into the system. As you can see in this intersection, the driver, they all behave, they drive legally, and there's no collision, basically. So that's a simple setup. Let's take a look at a slightly more complicated intersection of multiple lanes here. And if you pay close attention, the vehicle will be allowed to move forward and turn right, and then they can go to the left, just like in real life. And then the other road are allowed to enter the traffic. Let's go into a little more chaotic scenario. Here in a roundabout setup that you can see a vehicle of a different size enter and exit the roundabout smoothly. And they can use this roundabout to go right, go straight, go left, or make a U-turn. They look so happy driving. And as far as traffic simulation go, I think one of the most complicated scenario is the butterfly highway intersection. And from here, you can see that when the traffic coming in, take a look. You see the cursor here? All right. Take a look at this area. You see some of the vehicle merge in and enter the ramp. In the highway, they move at higher speed, and when they enter the ramp, they slow down. In this section, there's some collision avoidance going on, and they go all the way to the other side. And as you can also pay attention here, some of the vehicle will choose to merge in, some other will go straight, depends on their destination. So in terms of complexity, this project, I think, did quite well. However, do we have to trade complexity with scalability? Do we still have the massive scale similar to Unity demos? Let's take a look at a bigger test. You can also notice that this city loaded in immediately on this device. This is a 2016 phone. And that's because we use sub-scene streaming. I will talk about it later. Yeah, so we can wait for a bit for the traffic to form. Yeah, but basically, in my test, the performance is more or less bottlenecked by the GPU rather than the CPU. The rendering take bigger cost here. After we wait for a while, the traffic will form, and yeah, rush hour is coming. Yeah, so that is the result of the project. We now switch back to the slide. Oh yeah, then the asset I get from the asset store called Toon City. Yeah, so the second part of the presentation will be about how we do it, and I will go into a bit deeply into details. I will do a small recap about Unity ECS, and then go on the pathfinding section, the handling collision section, and talk a bit about generic parallel programming, end it with questions and comments. So as the name suggests, entity component system has three parts. The entity is basically your game object replacement. It makes up your game world, contains components, and in terms of implementation, in Unity ECS, it's just a single index number, an integer. And for component, it stores the entity's data, and when you combine all components together, it is actually the simulation state. And this is also the only place where you can store actual data here. And there's no logic, it's just data. In terms of implementation, it is modeled as a struct, which is a bit different from the regular C# class. You can only use simple split table type like a float, an int. Last time I tried, it doesn't even support string. So it's kind of simple in this term. The system is where the behavior I bring into the simulation. So what the system does is that it processes components and transforms them. It does that by querying, by filtering entities with a specific set of components. For example, if we have a hit point component attached to entity, and the damage system can query all the entity with a hit point component and check if it's less than 0, it's going to kill the entity. So that is the entity component system setup. And in Unity ECS, it is not required, but it's encouraged you to do more parallel programming to unlock the full potential. So in the regular Unity world, you mostly do sequential programming on the main thread. Let's say this guy is your main core CPU. What he does is that he will, let's say, go to the RAM to fetch some data. The distance between the RAM and the CPU is actually quite far compared to, let's say, L1 and L2 caches. And so in the main thread, you will basically go multiple places, fetching data and process them and put it back to the place you want. In the parallel world, the data are all coming in stream and tightly packed together, and they are fed into a bunch of worker threads that is very efficient in performing simple tasks at high speed and at large quantity. The input as well as the output are all arrays of data that you can fit into more and more worker threads. As you can see, the second setup is a lot more efficient. If that looks kind of complicated, you can just think like KFC, it looks similar. So in terms of programming, most of the time will be spent writing these so-called jobs. And the most popular job, at least in my project, is the iJob for each. With this syntax, you can specify which component you're interested in iterating. In this case, this job will iterate over all entity that has both the vehicle and the vehicle coordinate component and do some processing on it. You can further declare that some of the components are basically read-only. This will help the scheduler to put your job into the right place and avoid race condition. And so that is Unity ECS. So how do I break down the traffic simulator project into entity, component, and system? So first we have a bunch of entities that represent the road lanes and the traffic control point. I'll talk about the traffic control point later. And these entities will be fed into the traffic control system. The output will be the lane state, the state of each of the lane, whether they are enabled or disabled. The disabled lane does not allow incoming traffic. With these stateful lanes, together with the vehicle, they are fed into the pathfinding and collision handling system. The output will be the association of the vehicle and the road lanes, and where do they sit on the lanes. Basically, just a one-dimensional coordinate, one single number. Together with the splined data, because each of the road lane, they are not straight line, they are Bezier curve. These data together will convert the one-dimensional coordinate into a 3D coordinate that you have rotation and translation that will be fed into the rendering system. So basically, this is the whole picture of the traffic simulator project. So in this section, I will explain the pathfinding system. And when I was doing this project, I looked up on the internet. There's no pathfinding solution for Unity ECS that I could find. So instead, I look at a sequential algorithm and see which one I can adapt to be used in a Unity ECS way. So the most popular one that most people know is the A star. Basically, it gives you the path from point A to point B. And the advantage of it is that it has very low memory footprint. All you need is a closed list, an open list, and you do a heuristic algorithm on it. And these lists can even be reused from one path request to another. So it has very low memory footprint. However, it does not scale well. And in the scenario of a traffic simulation, we need a lot of path requests in a high frequency setup. The second algorithm I looked at is called FLOYD, which is quite popular in strategy games. The pros is that it scales well. It can give you all the paths from all sources to one single destination in one compute session. However, it is not really suitable for traffic simulation because in a hectic traffic setup, you have vehicle heading to different locations all the time. So kind of the only choice that I can take here is the FLOYD-WARSHALL algorithm. The pros is that it's instantly fast, give you the path for every single pair of sources and destination. Why is it so fast? Because basically it computes everything up front and store it in a huge cache. So out of these three algorithms, only the last one look suitable for the problems we have. However, it have big memory issues. First, I will recap about this algorithm. Let's say we have a network of n nodes. And for this algorithm, the complexity for building the cache is n powered by 3, which is very, very expensive. The cost of the cache memory is n power of 2, which is also expensive. And this is the pseudocode. It's actually quite simple to implement, basically just 3 for loop. And then you get the cache. So the problem here is the memory. And because n power of 2 is quite high, it is actually not suitable for a Metropolis setup. For example, we have, the obvious solution here is to divide the city into smaller sections, let's say a district, and then divide further to quarter and so on. Let's say we have a 1,000 by 1,000 node network, that's 1 million, that's a lot. And if we divide it into, let's say 10 sections of 100 each, the new cache size will be just 10% of the 1,000 by 1,000, which is a huge save. If we divide it further, we save even more. So within this section, let's say we divide it to 10 sections, and we receive a path request of a source and destination that sit in the same section. That is very lucky. We can simply just query the cache and give the answer. Just use the classic FLOYD-WARSHALL algorithm directly. The problem now is how do we perform pathfinding between different sections? And to further reduce the memory problems, we can apply some graph size reduction here. As I already said, we can divide the graph into connected sections, and we can see from here we have the orange section of the city, the red, the green, and so on. And we can also organize them into hierarchy. Let's say we have a high-speed highway network with this pink color here that connect the rest of the city. And in my implementation, I also discovered that more than half of the connection in the network basically had just one exit. For example, when you see this lane, when the vehicle leaves this lane, basically the only lane it can enter is the next one. So while this lane is necessary to compute the cache, after the cache is computed, we can throw away this lane out of the cache and thus reduce the cache a lot. Here will be an illustration of how do we perform pathfinding between different sections. Let's say we have multiple sections in the city connected by a highway network, and we try to perform pathfinding between these two orange points. So for each node in the section, I store the nearest entrance and nearest exit. Because when we look at this part, they have different address. Let's say this is quarter 3 and this quarter 2 of the same district. They belong to different quarter. And in order to have a path, you have to go up the hierarchy, go to the district. And when you are at here, the destination is now one level below, which means we need to work backward from the destination using the nearest entrance parameter that we pre-computed. And now the 2 points are on the same network. We can query the cache to get the path. And that complete the full path. And this pathfinding, we don't need to perform in advance of the movement. We can do it step by step. For example, here, it's from another network. Immediately, you go out of the network. And from here, and so on. So we divide the cost over time. I will give a small demo how this actually look in the game. Okay. All right. Yeah, so just a very weird looking city, but let's say we try to compute the path from this point to, let's say, here. As you can see, we have 2 small networks connected by the bigger road here. From this connection, there's no other information stored, so basically the only way we can do is go forward. And we are here, the pink line represents the nearest exit and the nearest entrance. Basically, in order to enter this small section, you have to go through here, and in order to exit it, you go through here. So the next point will be to exit it, to go to this point. From here, you are able to access this point. The path is available to you in the cache. Pay attention that you will be able to reach this point, which is in turn the nearest entrance of the destination. That closes the loop, and we have the path. So that's conclude the pathfinding section. We move to collision handling. And the requirements of the traffic simulation project is that vehicle must have variable length, and the lane segments also have variable length. And the ratio between the vehicle length and the lane segments can vary, which means one lane can fit in as many cars as possible, and at the same time, a very long bus can sit on top of a lot of lane segments. And this requirement basically break the solution of using dynamic buffer to store. Let's recap about dynamic buffer. Basically, it allows you to store an array per entity. However, there is a catch. It's not similar to your normal C# list, which can grow over time. The dynamic buffer, you have to provide the capacity in advance. And this requirement basically does not allow you to determine the capacity. For example, if we want to store all the vehicles in one lane segment, we don't know how many, because the lane segment can be as long as it wants to be. Of course, we we need this requirement that there's no collision within the same lanes, and also no collision when lanes are splitting or merging. So in the game, the road segments are modeled as a set of lanes. Let's take a look at this simple road segment. They have 2 lanes. Basically, each of them is a one-way connection and is also modeled as an entity. So you have 2 entities here, 2 lane segments. On the right side, you see a more complicated setup. We have total of 8 lanes in this road segment. So we go through each of the cases. how do we ensure that there's no collision when a vehicle enters a lane? So the basic theory behind this is that every time a vehicle makes a decision to move forward, let's say in a certain distance, x distance, this decision need to make sure that there will be no collision during this entire travel of the vehicle, mainly with the vehicle in front. Let's look at this scenario. We have a lane with a vehicle on it, and this is the length of the lane. We have 3 other vehicles. So in our system, the vehicle will perform pathfinding only when it reaches the end of the lane. So at this moment, this truck knows this will be the next lane that it needs to enter. And what it does is that it looks at this parameter called the enter space, which is the maximum distance that a vehicle can move toward that lane. And once the vehicle makes the movement, this space becomes the exclusive space, which means no other vehicle can enter. This will come again later. And the space it leaves behind is called the vacant space. So basically, for every lane that has a vacant space greater than 0, it means every vehicle in that lane should be moving forward its exact amount of distance. And we combine these parameters that make the lane component. The exclusive space is not needed because no other vehicle can enter this area. So how do we prevent collision when a vehicle entering splitting lanes? Basically, it exactly the same. Because the vehicle, when it moves one lane, it basically blocks the other lane. So there's no other vehicle that can enter the other lanes. The more tricky scenarios is when the lanes are merging. And at this point, we have to introduce another system to make sure that there's no collision between merging lanes. That is the traffic control system that I mentioned previously. It will come in multiple phases, and each phase has 3 states. The first state was that all the lanes that is merging will be blocked, so no vehicle can enter. Imagine that this is like a red light in the traffic light. And after this period of time, it will start to take in vehicle. It's similar to the green light. So the vehicle will start to move in. And after a certain period of time, this lane will be blocked again. And this phase will end the moment the last vehicle exits the lane. And we repeat to the next phase. But this turn, I will enable the lane below instead of the one above. And in that setup, all the intersection will have a smooth traffic. And yeah, so these are the illustration of some of our intersection. And the traffic control system, basically, you can specify which set of lanes should be enabled or disabled in some certain phases. For example, in this setup, if I remember correctly, like 2 of these will be enabled at one point, and that will help circulating the traffic around. In this example, it looks a bit messy, but we can divide it into multiple phases. For example, the first phase, every vehicle turning right and moving forward, they are not blocking each other, so they are allowed to go. And after that, they are blocked. These 2 are blocked. The one going left will be enabled. And after that, the other direction will be enabled. So there are 4 phases in this big intersection. Yeah, so that's how collision handling was done in the project. Now I move to the generic parallel programming. So let's look at this sample code again. We talk about data access here. So in this setup, you have a Unity ECS job that iterates on every entity with these 2 components, vehicle and vehicle coordinate. So these data you have in this parameter list are exclusive data. Unity ECS ensures that there is no race condition happening on these data because you are iterating on this entity. There's no other job, no other worker thread can access this data alongside with you. So you are free to write and read from all of these components that happen in this parameter list. Sometimes, in order to make things happen, you have to perform random access reading from so-called component data from entity. Random access is discouraged from Unity ECS because it kind of violates with memory locality, so it reduces cache efficiency. But there's a trick to recover that. I'll talk about it later. With this setup, if you forget to add this attribute, Unity ECS will complain to you. Basically, you have to add this attribute, and you can only read from this shared data. Why is that? Because ECS want to help you avoid race condition, because they are shared data. If you write to it, there would be a big problem. However, in order to create a convincing simulation, you need entity to interact with each other. And in that sense, a lot of cases, in a lot of the job that is required for the traffic simulation, we need the shared data that is writable. And in order to enable that, you have to add this very scary attribute, native, disable, parallel for restriction. And race condition could happen in this array if you're not careful. I will talk about how to avoid them in the next slide. So there are multiple ways a race condition could happen. The popular one is that you're trying to write the same address. Let's say we have this line in our job code that trying to write into an array element a new value. And because this is parallel programming, this line will be executed on multiple worker threads at once. And in some cases, we have two worker threads writing to the same entity, race condition will occur. And you ended up with unknown value. You don't know whether it's this one or this one. The trick to avoid this is to look at your simulation, at your setup, and try to figure out all one-to-one relationships that your inclusive data have. For example, in the traffic simulation setup, the setup that we designed, only one vehicle can enter a specific lane. Only one vehicle can exit a lane. This means if you write a job to iterate on every vehicle, you are sure that you can write into the lane that is about to enter or exit, because there's a one-to-one relationship here. There will be no collision. So in order to avoid race condition, you need to figure out all of these one-to-one relationships in your data, as many as possible. The second race condition is that you read and write at the same time to the same address. Because things happen in parallel, you don't know whether your read operation will be done first or your write operation will be done first. The value ended up in your memories will be unknown. A very simple example would be just this line of code. You try to read from this value and increase it right back. And because it's parallel programming, this can happen on multiple threads at once, and you end up with unknown data. The solution would be to do a buffer state. So you read from a place, and you write it to another place, and at the end of the frame, you write back to the correct place. Either that, or you have two array A and B, and the system will have a Boolean flag to work on A and then write to B, and then the next frame it work on B, right back to A. So that will avoid this type of race condition. And throughout the implementation of this project, I figured out this is the process that worked for me. So to write a parallel algorithm that do not have race condition, I first started writing the pseudocode on paper for the parallel algorithm, and look at the pseudocode trying to solve all the race condition, because we can just look at all the assignments, all the reading, and see if there is any race condition that could potentially happen, and we solve it in the pseudocode level. After that, I will not just implement it right away. I will only implement a sequential system version of that pseudocode, because in the current setup of Unity ECS, writing a parallel version of the system is a lot more time consuming, and it's very hard to refactor because there's a lot of boilerplate code. Luckily, in the last yesterday keynote, we have less boilerplate. And with this sequential system, we iterate until it works, because just like generic game programming experience, your code does not work on the first go, and you may miss some of the edge cases. So we need to iterate this sequential version until it covers all the edge cases, and only then I convert it to a job system. And here, a new problem would occur. Some of the race conditions that you miss in the pseudocode design process will show up here. So basically what I do is after I convert it to job system, I let it run for a long amount of time, and after, let's say after 5 minutes, weird things start to happen because of race condition. And in case you have too many race conditions that is not solvable, you can always split the job into multiple jobs, because race condition only happen per job. And in terms of component design, there's a dilemma. We never know how granular it needs to be to design a component. In my case, I will use a single view components as much as possible. For example, the land component I mentioned previously, we have a land length, enter space, and a vacate space of 3 fields. I basically use 3 components instead of 1 component with 3 fields. Why is that? Because when we perform a write instruction to a component, every single field is written, not just that field that you want. So it creates more chances of race condition. You have to check for all the 3 fields instead of just a field you want to write. All right, so in my experience, I figure out that I prefer to use single field components instead of combining multiple fields into one single component, because whenever you make a write operation, it's writing to the entire component instead of each individual field. And at the time of design and implementation, we never know which job require which components until they are all written and cover all the edge cases and work well. After that, we can always combine the components that always go together. Why do we do this? Because syntax-wise, Unity ECS give you a lot of support if you write a job with 5, I remember correctly, only 5 components or less. If you need more than that, you have to write a lot of stuff yourself, like the querying and everything. And another tips was to avoid the command buffer as much as possible. So command buffer is used for structural changes, because in the job that you write, they will iterate through the entities a lot. And that's why the data layout needs to be very efficient. And whenever you want to add an entity, you want to add a component, remove component, it changes the structure of this very efficient data layout. And that will need to go into a buffer to be performed at the end of the frame. However, we might fall into a pitfall of writing a very complicated parallel job just to populate this command buffer. And this command buffer is executed sequentially anyway, so we shouldn't do this in the first place. And Unity ECS also gives you a lot of batch operation that can be performed sequentially. That's also very efficient. For example, if you want to add components, you can do the batch operation from the entity manager, leave it at the default values, and do a job to set the component values. And this way, you avoid the command buffer altogether. And you should use subscene for faster scene loading. As you can see in the demo, the big city was loaded in immediately. You can look at the mega city project to see how it's implemented. We also override the game object conversion system to do the FLOYD-WARSHALL cache computation offline. So even with the big city, you can start right away because the cache is already stored in the entity. And as I talked previously, we use a lot of random access through component data by entity, and that defeat the cache efficiency. However, you can gain that back by using share component to group entity that is related. For example, during pathfinding, from when we iterate from one land, we do a random access to another land. However, we use share component to group all the land within the same section together. So the pathfinding in the pathfinding setting, we only look to the lands that is close to, physically close to your current land. And with this share component, we don't perform any logic on it, but it helps to group this entity into the same chunk that fit into your cache. And in this way, you still have cache efficiency at the same time as random access memory. And at first, when I write the traffic simulation, I use floating point, and that's a very big mistake. So race condition avoidance, the method that I use have strong assumption on one-to-one exclusivity, and those assumptions do not hold when our floating points value accumulate error over time. So I think my suggestion would be to write everything using integer instead of floating point. Yeah, so that's our presentation. If we still have time for questions. Please. So if you don't use the scary attribute that I mentioned in the slide, there will be no rate condition because you only read from the shared data. Either that or you operate on the exclusive data that there's no rate condition whatsoever that Unity ECS provide you with. So in my case, I deliberately access the shared data and enable writing to it. And in order to do this, we need to be fully aware that race condition could happen. And my method would be to look at your data setup, to look at whatever information you have in your problem, to see the strong one-to-one connection between your data. For example, in my case, one vehicle can only enter one specific lane at a time. Two vehicles cannot enter one lane. So that's like a strong one-to-one connection, and when you iterate on the vehicle, you are freely able to write new state to the connection that is about to enter, and there will be no race condition occur because of this one-to-one connection. So that I will need to check with my company. Any other question? Thank you a lot.